Okay, the last topic of this chapter deals with what we call free fall. What happens when you drop an object? Well, obviously it drops to the ground, it travels down. But does it stay the same speed as it's going down? Well, when it left your hand, it was not moving at all. And by the time it hits the ground, it's going something faster than zero, so there has to be an acceleration involved. And understanding these questions helps you understand how we were able to figure out what the concept of free fall is in terms of mathematical relationships with A. The fact that the object is being pulled towards the center of the earth is pretty much how gravity works. We're all getting pulled down to the center of the earth. If we didn't have the foundation that we're standing on, we'd all get sucked down to the center of the earth and we would get burned up in the inferno that is the center of the earth. However, we do have a foundation, so we're not going to worry about that. But we do know that it's not moving at a constant velocity. So all those formulas we've had up to this point with A is going to apply with G. But the nice thing about this is that the acceleration, for the most part, except for maybe 5, 6, 7, 8, 9 decimal places will change, not enough that we really care. And so we're going to go with that. And it's 9.80 meters per second squared. Now, I'm hearing that there's an adjustment now to 9.81 meters per second squared. So if you go to college, university, and they give you 9.81 instead of 9.80, no big deal. But we're going to use 9.80 because it's a nice number to work with. In terms of English measurements, the acceleration is 32 feet per second squared, or 32 feet per second for every second it drops. We're going to be using the 9.80 most of the time, but keep in mind that 32 feet per second squared is the equivalent dropping acceleration for gravity in the English units. Okay, so in calculating the velocity of a free-falling object, we use the formula G equals delta V over T instead of A equals delta V over T, knowing that G is going to be 9.80 meters per second squared. And so if we have the formula G equals delta V minus, which is VF minus VI over T, we multiply both sides by T, you get VF minus VI equal to GT, and then we add VI over, and we get this formula. So this is now a new formula we can use for our physics toolbox. If we want to find the final velocity of a dropping object, we take its initial velocity, which most of the time will be 0, plus the gravitational acceleration times the amount of time it took to drop. Now, if you throw an object down, you have to know the speed at which you threw the object. That'll be your initial velocity. But if you just let it drop, that's always going to be 0. Okay? So that's exactly the same thing as VF equals VI plus AT. We can use that with a non-free fall situation. So all these can be put in your physics toolbox. Again, I don't do a lot of memorizing formulas. It's not my thing. But if your thing is memorization, which means you probably like biology, no problem. Go ahead and do that. But I like to rely on my algebra. So here's an example. A rock is dropped off a cliff that is 16.5 meters high. What is the time it will take for the rock to hit the ground? And how fast is it traveling when that happens? Okay, so we know that D equals 1/2 AT squared, and that A in this case is G, so we really should have G there. So 16.5 meters is the height of the cliff, so we know that's the distance we're dealing with. 1/2 is 0.5, A or G is 9.80 meters per second squared, times the unknown T squared. 1/2 of 9.80 is 4.90. And we're going to divide both sides by 4.90 to get T squared by itself, and we get 3.37. Take the square root of both sides, and the time it takes for the rock to hit the bottom will be 1.84 seconds. Then the next question is, how fast is it traveling when that happens? Well, again, we're going to use delta V equals A times T, because the initial velocity is 0, that drops out. And A is gravitational acceleration, so again, I could have used G there, but it's the same thing. 9.80 meters per second squared is the acceleration, 1.84 seconds is the time it drops. So we know that at the instant that rock hits the ground, the speed is going to be 18.0 meters per second. And if it's like a rock, it's not going to be affected by wind or anything like that. It's going to fall at a pretty consistent rate at 9.80. So this is the same kind of stuff we've had up to this point, just now we're using G for A. So your practice problems are right here. Good luck.